Let us now introduce glancing collisions in this video. Now, all the collisions that we've looked at so far were all head-on collisions. They were all happening in one dimension. Okay, an object would come and it would move in one direction, it would collide with a second object moving in another direction, and then they would continue to move. After the collision, they would continue to move along this straight line, okay, whether in the same direction or opposite direction and all that, that all depended on the mass and the velocity and all that. But they continued to move in the same direction, okay. But now, what we're going to do is we're interested in looking at collisions where things are not moving in the same direction, okay. What happens if in a collision, things collide and then they move along completely different directions? So we look at the glancing collisions in two dimensions and figure out what's happening. Okay, so let's say that I have an object that is moving to the left. I have another object that is moving to the right, and let's call this one 1 and let's call this one 2. And what happens is that after they collide, okay, so let's say they collide somewhere here in the middle, and after they collide, one will continue to move along some direction that is, let me just show it with some red ink there. So one goes here, and then blue starts to move along this direction. Okay, so this is object number 2 that will move along some random direction. So they're both moving in directions, okay, in any direction possible. If you were to draw an axis there, the motion would be along, would not be contained to a line. Okay, it's basically, let's look at some two-dimensional collisions. Okay, so our question is, how do you address this? How do you figure out where they're all going to go? Okay, I'm just going to redraw this thing here so that it makes a little more sense. So they collide somewhere in the middle here, and then after the collision, one goes here, and let's say that, just for purposes of this, there are two moves in this direction, and we're going to figure out what happens in the collision. What do you do? Okay, so now once again, our tact is going to be similar to what we've had earlier. Alright, if nothing's been told about the collision, if you do not know whether it's elastic or inelastic, we'll assume that the collision is not elastic. So we will not assume kinetic energy conservation. That's just a higher, a higher kind of restriction that we put in the system. But here we'll just say that, hey, if the collision is if it's just a collision which may or may not be elastic, okay, then once again, because during the collision all the forces are internal, we can assume the momentum conservation. So we know that Pi will be equal to Pf. And now here the vector nature of the momentum becomes extremely important, because if we, things are happening in two dimensions, so we'll have to break everything into components and then make sure that we conserve the components along the x's and along the y's. Okay, so this simple statement here implies that Pix is equal to Pfx, which means the total momentum along the x is equal to the total momentum along the y, and it implies, the total initial momentum along the x is equal to the total final momentum along the x, and the total initial momentum along the y is equal to the total final momentum along the y. Okay, so that's what the momentum conservation says. Now, if in addition to this, if the collision is also elastic, then we also have the kinetic energy conservation. Okay, so we have essentially three sets of equations that we can use to figure out what how everything, the velocities at the end, and also in this problem we'll also have to figure out what angles things are moving. So a lot of information needs to be given in order for us to be able to do anything with it. Okay, so let us set up an example and see how to go about doing this. So let's take a simple one first. So let's say we have a vehicle of mass, say 1000 kg, that is moving due east at say 15 meters per second. Okay, and let us say that there's another vehicle of mass 1500 kg moving at say 20 meters per second. Okay, now these two, they collide. Okay, they collide somewhere here, and then after the collision, let's say that they move in some direction. Okay, and our goal is to figure out the we want to know the speed with which they travel together, and also the angle at which they will move. Okay, so in this way we have two unknowns, and we're assuming that they're basically going to get entangled. Okay, so we're simplifying the problem. So they're going to get stuck together and they're going to move together as one unit, and our goal is to find the velocity, which implies finding the speed and also finding the direction in which they travel. Okay, so clearly we recognize that this is an inelastic collision problem, so we cannot assume kinetic energy conservation, but we'll go back to we're going to use Pi equals Pf. Momentum is going to be conserved in this problem. Okay, and in order to do this, once again, what we'll do is we'll do Pi equals Pf along the x direction. So we'll do first Pix is equal to Pfx. Okay, that's what we'll use. So in the beginning, let's look at the momentum along the x direction. Okay, the only object that is moving along the x direction in this problem is a 1000 kg vehicle, and it is going to have a momentum of 1000 times 15. Okay, the x momentum of the 1500 kg vehicle is 0 because it is only moving along the y direction in the beginning. Now, that gives us all our initial momentum. The final momentum, on the other hand, since they're going to move as one unit, the mass is 2500, the speed is v. So the momentum itself is 2500 v, but along the x direction, we have 2500 times v cosine theta. Alright, so this is momentum conservation along the x direction. Let us repeat this for the y direction. Piy is equal to Pfy. And what we have is we have 1000 times 0, because the first guy is not moving along the y direction, plus 1500 times 20, and this is equal to 2500 times v times sine of theta. Alright, so we have a lot of information here. Now we need to solve the two equations for the two unknowns. So the first equation gives me 1500 equals 2500 v cosine theta, and the second equation basically gives me 30,000 equals 2500 times v cosine theta. Now I can simplify, I can divide both sides by 2500 and get v cosine theta equals 6, and then this guy gives me, I can do the same thing here, and this gives me v sine theta equals 12. Alright, so we're in business now, we can figure out the rest of the stuff. Okay, so we have v cosine theta equals 6, v sine theta is equal to 12. Now we can solve these two equations, which is much easier to deal with, and the best way to go about this is, if you look at the equation, that we can find v from one and plug into the other. We can do something simple here. We can do v sine theta divided by v cosine theta equals 12 divided by 6. Okay, and this basically takes care of the v's cancel out, and I end up getting tangent of theta equals 2, and this gives me theta equals arctan of 2. Okay, we can find that number and take care of that. Okay, once we know this, then we can then find v equals 12 divided by sine theta, okay, by plugging in the value of theta from this equation. Alright, and if you calculate all this correctly, you get about 13.4 meters per second. The angle here comes out to be about 63 degrees, and then when you plug that into this equation, this will give you a value of 13.4 meters per second. Okay, so simple application of a glancing collision problem. We just used momentum conservation, but because we have two directions to deal with, when we conserve momentum, we'll have to conserve it along the x direction and along the y direction. Okay, that's it for this one.